Okay, this is where the new element begins when we're looking at Fourier series. So we're going to take a look at now what's called the exponential form of the Fourier series. So you are familiar with the trigonometric form of the Fourier series using cosines and sines and these expressions for figuring out the coefficients that go along with each of those given x. But we know that cosine and sine can both be expressed with complex exponentials. So this comes from Euler's formula. So if we take a look at this, you'll note we're summing complex exponentials. Here we are subtracting them. And of course there's a complex valued j here. Okay, so if I take a look at what for each k, if I sum those two up, what do I get? And I collect like terms, then I have a complex exponential at jk omega naught and a complex exponential at minus jk omega naught. And these are the constants in front of them. Those are complex valued constants, and we can call those c of k and c of minus k. And using that and taking a look at how that affects the sums, we can actually write our Fourier series in a much more compact form. So first off, notice that we are now going from minus infinity to infinity instead of 1 to infinity. But that ends up summing over both the positive and negative values of the complex exponential. And then what do our coefficients look like? Well, we're still integrating over one period, and now all we're doing is we're projecting x onto a single component. And there's a negative sign here. The reason that that negative sign has to show up is because it is an inner product, and when you're talking about complex valued functions, you need to multiply something times its conjugate, or something times the conjugate of something to define a proper inner product. So that's why that negative sign shows up there. And there's a relationship between the coefficients of the exponential form of the Fourier series and the coefficients of the trigonometric form of the Fourier series. Note that the trigonometric coefficients are all real. The exponential coefficients can be complex valued. They might have only a real part, they might have only an imaginary part. In general, they're complex valued. And like with all complex numbers, we can represent those in either a Cartesian form or a polar form with magnitude and phase. So let's return to that binary pulse train and take a look at our exponential Fourier series and what the coefficients look like for successive approximations. So we're going to approximate with a single complex exponential. So we're going to take k equal to 1. We want to figure out what c1 is equal to. Well, we just follow what the integral tells us. So we write these expressions down. So notice it's 1. Oops, sorry. It's 1. The signal itself is 1, or a, halfway through the period, and then it's negative a for the rest of it. Now we're just integrating exponentials, which are fairly straightforward. What you get might need some manipulation. So now we have complex valued elements in here, and so we have to add real and real and imaginary and imaginary. Okay, so let's just concentrate on this third line to start with. So note that omega naught is equal to 2 pi over t naught. So we're going to get 2 pi over t naught multiplied by t naught over 2. What we end up with is negative j pi. And then this one becomes negative j2 pi. This one is negative j pi. So now what are the values of those? So in general, they could be anything, but remember that that e to the jx is actually always on the unit circle in the complex plane. The point on the real axis is equal to 1 or minus 1, the point on the imaginary axis is either j or minus j. So this is at an angle of minus pi, which is all the way over here, so it's actually equal to minus 1. This is equal to 2 pi, so we've basically gone all the way around and returned back to 1. This is equal to minus 1 as well. And so when you solve all of that, you just get this for the first coefficient in the exponential Fourier series of this binary pulse. This is comforting because remember that we found this for the value of the coefficient for the trig form, and you'll notice this is 1/2 of that, or the magnitude is 1/2 of that, which is what we expected from our derivation on the last slide. Let's just compare the two. So the trigonometric Fourier series and exponential Fourier series are shown. The trigonometric Fourier series, the basis functions are trigonometric, cosine and sine, which are always real valued. The expansion coefficients, a and b, are also real valued. The frequencies represented range from 0 to infinity. In the exponential Fourier series, the basis functions are phasors, which are complex valued. The expansion coefficients are complex valued. And because k is going from minus infinity to infinity, the frequencies that we're representing are actually ranging from negative infinity to infinity. Well, what does negative frequency mean? Well, in order to understand that, let's just consider the spectra of the single tone signal. So this is the simplest possible periodic signal we can think of. So that would be a cosine and a sine. And I've used their Euler formulas as well, just to show what happens here. Okay, so the trigonometric series is given by that. But if you compare that with our cosine and with our sine, we really just end up with one single term out of all of these terms in the Fourier series. In the exponential Fourier series, for each of those, now we take a look at these equivalent forms here, we notice that there's only 2 terms out of the whole series in this one, and only 2 terms, in fact the same 2 terms, in the Fourier series for this one. It's just their amplitudes, or the coefficients, are slightly different. Okay, so let's graph the spectra of both the cosine and the sine for both the Fourier series and the exponential Fourier series. So what we're doing is we're graphing the values of the coefficients. Well, there's only one coefficient, and it has an amplitude of a for the cosine. What does the exponential Fourier series look like? Well, it's got 2 terms, and both of them have an amplitude. I should have an a in here actually. So they have an amplitude of a over 2. Okay? One of them is at k equals 1. One of them is at k equals minus 1. And we also have to have a phase because it is, in general, a complex value. So it's got a magnitude or amplitude. Each term is only a over 2. And the phase is just 0 because it's strictly real valued. What about the sinusoid? So the sinusoid has a single coefficient in the trigonometric Fourier series, so the spectrum would look like that. For the exponential Fourier series, note that this first one has a coefficient of 1 over 2j, or in other words, if we multiply by j on the top and j on the bottom, we have minus j over 2. Well, minus j is actually over here, so that's at an angle of minus pi over 2. So this first term actually has a phase of minus pi over 2. And this other one has a phase of plus pi over 2. The amplitudes are still the same. So for the exponential Fourier series, when you're graphing the spectra, you have to show both amplitude and phase. And the spectra of single tones are extremely important ones to remember. They're used all the time for designing communication systems or other types of systems. finally, let's just summarize some of these concepts. So we want to understand, in general, how to decompose and analyze signals in different ways. And we're basically using these basis functions, and then the information is stored in the coefficients. For a Fourier series, the basis functions are either sinusoids or phasors at different frequencies. This allows us to analyze a signal for its frequency components, and so we get a frequency domain perspective of the signal. What's that going to allow us to do? Well, that's going to allow us to analyze a linear time invariant system in the frequency domain. And the fundamental basis behind all of that is, if the input is one of these basis functions, what's the response of the system? You may recall when we did time domain analysis, we have said, what is the response to a single impulse? What do we get? Here we're doing, what is the response to a single phasor? What do we get? And that's where we're going to leave it for now.